Hello, everybody. Are you nice and awake? Didn't think so. So what I'm going to do is I'm going to present some thoughts that I've got, and I'm going to ask you some questions, and then there's some link to some Padlets so you can have some conversations amongst yourselves and hopefully jot some things down. But this is a very loose, no, I wouldn't really call this a session. This is a stream of conscious that I've got that I want you to join in with. So let's see how we go. First of all, I'll introduce myself. So my name's Matt Bawn. I'm from a little tiny place in the middle of England. Then I did my first degree in the University of Wales, Aberystwyth, but in physics. Then after that, I worked in industry for about 8 years, installing high-field superconducting magnets for research purposes. Then I went to UEA to fix one of their magnets, and they offered me a PhD, so I did a PhD in biochemical spectroscopy. Towards the end of that PhD, my now wife became pregnant, but she was living in New York, so I had to move to New York and found a postdoc in biomolecular spectroscopy. But then she needed to go to Peru to do some field work. She's an anthropologist. So then I had to move to Peru, where they didn't have biomechanical spectroscopy. So I taught myself bioinformatics and set up a bioinformatics capability in a human genetics lab. I realized that I preferred genomics to spectroscopy. And so when we decided to move back to the UK, I found a job in genomics, but particularly in bacterial genomics at two BBSRC-funded institutes in Norwich, the Earlham Institute and the Quadram Institute, broadly using computational methods to analyze genomic sequences. And then in 2022, I moved to University of Leeds, where I became a lecturer in bacterial genomics. But at that time, my wife was a lecturer in Newcastle, so I've just moved to Newcastle in September, where I'm a senior lecturer in microbial genomics, broadly using computational ways to do my research, but also thinking about digital methods in the biology curriculum. So why have I told you this? This is how anthropologists present themselves, because it surfaces my biases. So I'm going to be talking about digital skills, and I'm talking about that because I think they're important. I think they're important because it's my job. So please feel free to disagree with anything I'm about to say. So this is some feedback from a module that I developed at Leeds, which was a first attempt to introduce second-year undergraduate biologists or bioscience students to ways of analysing genomic data. So I asked them a question: please give me some words associated with omics. And you can see they've got a lovely word cloud, and in the middle of that word cloud, we see the word data. That's all I want to say about that at the moment. And if we look at the growth in biological data, what we can see is it's pretty much exponential. So this is a picture showing the growth in GenBank sequences available from, say, 1990 to pretty much the present day, and the number of users. So I think we're all aware we're getting more and more data. And what I mean by data in this sense is digital data. What is digital data? It is data that pretty much can be represented by a text file. You could open up digital data in Notepad and you could see something there. Now, the fact that this is digital in this text format means that it is easily shareable. It is easy to put on a database and it is easy to access from out the world. That means we're transitioning from an area where traditionally people would have to create their own data to an area where people can use other people's data because it is so shareable. And why am I going on about data? It's because data and digital skills are intrinsically linked. When we talk about digital skills, or let's say, when I talk about digital skills, what I'm talking about is the skills that students or researchers need to be able to access that data and do something useful with it. Now, that something useful could be something useful in research, or that something useful could be something useful for students to pick up other skills in biology. Of course, we're also thinking about the futures of our undergraduates, and I'm going to specifically route what I'm saying to the undergraduate curriculum, because what I believe is we need to prepare undergraduates for masters or for employment with some sort of concepts around digital and data. And these are some predicted growth in biotech trends. And I think that the main point I want to point out from this is that the top two are big data and artificial intelligence, intrinsically linked to data, but also we've got things like precision medicine and gene editing, also linked to data. So if we believe that we're preparing bioscience graduates for future employability, we should also consider that they're probably going to enter a world of employment that will call them to be somehow literate with data and digital. Hopefully that's not contentious. Shakies, noddies? No? So, biology and data. I would argue that biology is at the heart of many of our current and future grand challenges as a society. Food security, human disease, as well as like antimicrobial resistance. These are all problems that we will need to face, and they are at the center of biology. And, as I've sort of pointed out, we're increasingly generating larger and larger amounts of data in these areas. So, biology is becoming one of these big data areas. So we should, therefore, equip biologists with the skills to be able to use that and be useful to society and themselves. So this is a thought for you to think about, not quite yet, but just to whet your appetites. What do you think are the types of digital skills that we should be teaching, and how should we teach them? So one of the things that I was thinking is, I've often sat in rooms where people mention things like Microsoft Office as a digital skill. Now, as someone who analyzes data, do we teach students to use Word when we ask them to write essays? Not necessarily. We sort of put that different. So the general question I want to let you think about is, how much IT should there be in digital, for example? Just think about that. Another sort of issue we have with biologists is there's quite a lot of differences amongst the biologists. So we may or may not have students that have studied maths. We probably don't have students that have done very much computation. So how can we create a framework where we're enabling all of those different types of students to approach these skills equitably? You know, think about that a little bit. This is from quite an old paper, so maybe 10 years ago, where some bioinformaticians were thinking about what are the core competencies that bioinformaticians should have. And what you can see is there's lots of different things there. So there's biology, obviously, computational biology. But some of the things that often we don't think about is there's also things, where's my favorite? Visualization. So as you get more and more data, as a computational biologist, the challenging thing is being able to present that data in such a way that your conclusions become obvious to the person looking at that data. Now that's a completely, so far, I've not seen this taught at an undergraduate level. How do you present data in an effective way isn't built up as much as I hope it might be. And there, of course, you can go on the internet, you can find different vignettes showing you with this type of data, this is a good way. But also, as we, as researchers, are generating more data, this is sort of a mutable area anyway. We are creating our new plots. So how can you reflect differences in research in a sustainable way into a curriculum? Other things are there is obviously quite often when people think about digital skills, they're thinking about programming, for example. So are there some specific programming languages we should be using? How are we introducing them to students? But fundamentally, how should we be teaching programming? So when I was at Leeds, I asked the computer science faculty how they taught large cohorts of undergraduate students computer programming languages in person, and the response was they tried to avoid it. So if you think about your own universities, if you were to try and teach programming in a computer cluster, how big are your computer clusters? They're typically around 100 computers, but we might have cohorts of 300. Is it sustainable for us to run the same session 3 times? Do we want to run it 3 times? So how should we do it? Because the best practice in computer science and teaching coding is live in-person coding. What does that mean? That means that you stand in front of a group of people typing into a screen your code so that they can follow along. The reason it's done this way is it slows you down as a presenter and it enables students to see that you can make mistakes and that's fine. So that's why it's the best practice. And so here's something for you, please, to do in your groups on your tables. It's a little activity, and hopefully this QR code will take you to a Padlet, which will hopefully work. If it doesn't work, then we'll think of something else. But think, what are your current taught digital or data competencies, and where do these sit in your curricula? Is that first year, second year? Have you got a planned learning journey for digital competencies? And are there any gaps that you've got so far? So what time have we got? We've got, yeah, if you could spend maybe 5 minutes on this and try and fill out the Padlets, and if we've got time, I might ask you to throw some ideas at me if that's fine. Yep. Right, I'm going to move on now because there's another activity coming up which for me is more interesting. So if you think of something, feel free to jot it down whenever. This link is going to stay live. What I'm going to do is, there's only one thing there. Oh, look at that, it popped in for no reason. So, you might recognize the scientific method picture. So, you have an observation in your sort of chosen area, and that's giving you some sort of idea or hypothesis that you wish to test. You test it with an experiment, you analyze that data, and that informs the way you view the world. This is the traditional way that science has been done. However, with data, our methods of doing science are changing somewhat towards data-driven research, which means that with large amounts of data, you do some data analysis first, which informs how you view that problem. Right? It sounds very similar, but the approach is somewhat philosophically different. And when we look at how these two different types of doing research, where they're performed, yes, in academia, the way that we get funding for our research is very much based on hypothesis-driven research. If you want to get money, you start off saying your research question, the hypothesis which you're going to test is. That is the traditional way we've done it. However, increasingly, in industry, there's more like large data projects where you would start off analyzing as much data as you can to go that way. So, where am I going with this? It's if the way that science has been done is somewhat changing in research and in industry, how much are we taking that into consideration when we teach our students how to do science? And when we think about doing science as well, I know the first diagram I showed was the increase in genomic sequence available. Beyond genome sequences, there are other types of data being generated. Obviously, different types of omics data, RNA data, metabolomics, proteomics, but beyond that, other types of data like visualization data. So, are we creating the space in the undergraduate curriculum for students to approach their questions by integrating different types of data? This is not an easy problem. I had a meeting yesterday with some researchers where we were thinking of ways to try and integrate different types of data, and those methods aren't robust enough yet in research, but we still need to say to undergraduates how to think about doing that in the future. So this is an idea I had when I was at Leeds, and I've put a picture of Bonnie up here. When I was doing my postdoc in New York, Bonnie was doing a PhD in computational chemistry, and she decided, probably wisely, not to stay in academia, and so she worked in industry. And she worked for GSK, but now she's currently head of artificial intelligence for research at Microsoft, so she's a partner at Microsoft. And so she leads a global team of hundreds of researchers doing quite well. And when I was thinking about digital skills, I asked Bonnie for a conversation. I said, if you were employing a bioscience graduate, what key skills would you want? And I was expecting, Python, the ability to... No, what she said was, as an initial thing, just some sort of understanding where the data's come from. Right? And so what I was thinking about is, you can teach undergraduates, you can give them lots of modules from every stage of their degree, but unless it makes sense, unless there's a thread through that learning journey, they might miss the point. And so I was trying to think of a way of building up. So you could imagine a journey for them. So this is just an idea of how they build up their journey through data with grammar. And by grammar, I mean things like databases, different types of platforms, different types of languages. So they get an idea of the rules by which data might work. Then they can start building up that towards answering questions. So this is why I've put logic there. So by using this language on those databases, we can start answering some questions towards the third level rhetoric, where you can start influencing people through using data. This is very much like a final year project. So at least if they haven't understood anything, they will have a general understanding of why and where that data's come from. So I've just put that down there. But this leads to a thought. Again, I'll make it more concrete. How are we preparing undergraduates to deal with these types of complexity in data? And by complexity, I mean different types from different sources, but also different ways of using this data-led approach versus hypothesis approach. Some thought. So this goes to my last activity for you all, and I hope again that the Padlet works, to start thinking about that. Please, can you let me know, in your experience, how you're incorporating these new ways of doing science into your curricula? And there's some prompt questions there for you to think about. Is that fine? Carry on talking. Oh, that's nice of you all to hush so preparedly. So, hope you found that fun. Yes, good. Thank you. Oh, well, you can't win them all. So, yeah, I've put a slide, even though I don't know really what I want to say about this. I think the key themes that I want to repeat again, we're getting more and more data, and we need to teach students how to use that data. And I don't think that we're necessarily building in this new way of thinking into our curricula. And I'm not saying it's easy to do that. That's the beginning of the conversation, isn't it? What does the future hold? And I've put that immediately above AI. And of course, AI is a big thing, and it's going to continue to be a big thing. I will mention a story that I saw, whereas Google's just launched, I think they call it the AI co-scientist. And a scientist, a London scientist who works in microbiology, asked a question about his research to the Google AI scientist based on his 10 years of research. And within 2 days, Google co-scientists had proposed 4 hypotheses related to this question, one of which was the one that this scientist had come up with after 10 years of research. And the Google AI scientist did it in 2 days, but not only that, had produced 3 equally plausible alternative hypotheses, one of which that scientist had not considered. So while last year we had at this conference a Gen AI session thinking, oh, well, you know, that's all very well, but that's mostly for things like writing essays. Us intellectuals might not affect us because we're so creative thinkers that we're still aloof from that. Maybe not, but I'm sure this is going to be something that we will need to build in a more research-based way. And you know, I've asked you to think about this in terms of the undergraduate curriculum. What is the balance between undergraduate and taught masters? Because sometimes I get the feeling that we create masters maybe to get over some of the things that we wish we'd done better in the bachelors, if you know what I mean. And at a certain level, it's almost, I've heard before that the masters are the new undergraduate. But how long can we expect students to keep on doing more and more higher qualifications to be able to go into a job? Who knows? And what's the role of industry in all of this? I mean, it's sometimes you have useful conversations with industry and they can tell you exactly what they're planning. Sometimes when you have conversations with the industry, they don't know what they're planning. But we do need to take that in consideration. Maybe one way would be in our final year projects to open that up to industry so that they're always up to date. More questions. And I think that's all I really wanted to say about that. Thank you.